Today we're going to look at direct proportion, and you might already think you've got an understanding of it, or you might think, what do these words mean? Today I'm going to explain what they mean. Okay, we're going to start out with this recipe here for a pancake mix. Pancakes, you need some flour, you need some milk, you need some salt, and an egg. We want to make 10 pancakes. We've got the recipe for 4, so how much flour do we need and how much milk do you need? Pause the video and try and answer this. So this sort of question, I would work out how much one pancake needs. That was not meant to happen. And so to get that, I can just divide through by 4. So if I need 6 dessert spoons of flour for 4 pancakes, I'm going to work out what one pancake is. It's going to be 6 divided by 4, which is 1.5. And then the milk is going to be 1/4 divided by 4, and that's actually going to be 1/16. We then want to know for 10 pancakes, so I'm going to multiply through by 10. So I'm going to need 15 dessert spoons of flour, and the milk is going to be 1/16 divided by 10, which I can sense is not, oh no, it's not too bad a number, 0.625 of litres of milk. So we can figure these things out. Okay, that was just a little starter, because what the main thing I want us to do is plot the number of pancakes against the number of dessert spoons, as shown on this graph. So what I'd like you to do is have a go at this. You're going to have to draw your own axes in a similar sort of way, and then attempt it. Okay, so I'm going to have a go at it. Actually, I've done one earlier because I want to save a bit of time. So this is what I did. I've plotted 6 dessert spoons against 4, and then I have both of those to give me 3 and 2, and I even plotted 0, 0. If I have 0 spoons, dessert spoons of flour, I can't make any pancakes, really, like not properly. And I see if I connect them that I get a straight line. And this is an example of direct proportion. So when we say direct proportion, we are saying we get a straight line through the origin. If we want to get a little bit more technical, then we can write this down as an equation. Any straight line that goes to the origin can be written as y equals mx. Yeah, the general formula for a straight line is y equals mx plus c, but here the constant is going to be 0. So this is going to be our formula when y is directly proportional to x. Sometimes you see people write y equals kx because we sort of move away from the gradient, but it is the gradient that's going on here. And if we were to work out the gradient, we would see actually I'm going along 6, I'm going up 4. So my rise over run is going to be 4 over 6, and in this case it's going to be y equals 2/3 x. One other thing to say for direct proportion is as one doubles, the other doubles. So like I did here, if I've got, as one halves, the other one halves. If I've got 3 dessert spoons of flour, I get 2 pancakes. If I double that, I get back to my 6 and 4. If I double again, it'd be 12 and 8. That makes sense as a recipe, doesn't it? You can't double the amount of flour and suddenly make loads more pancakes, and you're not just going to make like one more. So that'll be another thing to write down as one doubles, the other doubles. This can be extended to say as one triples, the other triples, or they both change by the same percentage each time. I'm going to write that down actually. So they change by the same percentage. Please write this down as well. So that is it. That's quite a lot of information. But we've looked at a recipe. It's a classic example of direct proportion. The more, so I double my ingredients, I can double the amount that I get out. In this case, pancakes. I get a line y equals mx or y equals kx. That describes the straight line that I get that goes through the origin. And just the other thing to think about is there's one doubles, the other doubles, or you might say they change by the same percentage. If one increases by 40%, the other increases by 40%, and so on. That's a more general way of saying it. Okay, we're going to look at a second example. We're going to look at paint prices. So we've got the 1 litre of paint costs £15. We're going to assume the prices are proportional to the amount of paint in the can. That's the same really as us saying there is direct proportion going on, as one doubles, the other doubles. In reality, that doesn't tend to be the case because you tend to get more from your money the more you buy. But here we're not assuming that, we're saying they are directly proportional. So I would like you to work out the prices of these other pots of paint and then plot the price of paint against the volume of paint and think about what conclusions you can make. Okay, so if we do this, then we basically, to work out what 2.5 litres would cost, I would multiply my 15 by 2.5. To work out what 0.75 costs, I would multiply my 15 by 0.75 because I've got my unit of measurement here. And this is what you should get, these values here. And if you plot that, which I've already done, then you will again get a straight line. I kind of gave it away. When I said what conclusions can you make, we want to conclude that they are directly proportional. Now the question basically told us this, but I wanted those words to go through your brain. Directly proportional. That means we're going to get y equals kx. And in this case, we see as we go along 1, I go up 15. So actually y equals 15x. I might even write more in words that the volume, I don't need to use y and x. The volume is 15. Sorry, I made a mistake there. The price is 15 times the volume. Okay, and on the first example, well, I called them y and x in that case. I've sort of done that here, but yeah, I'm writing a more generally wordy formula here. So this is a second example of direct proportion. Third example of direct proportion, we are going to be stepping up a little bit now. So what I want you to do is find the areas of circles with radii, that's plural for radius, of 0, 0.5, 1, 1.5, and 2. And then I want you to plot the area versus the radius as shown below. Have a go at that now, please. So to do this, you need to use the fact that a is pi r squared, and then it's a simple case of substituting in your radius into this formula. So when r is 0.5, we're going to get that a is pi times 0.5 squared, and I can substitute that into my calculator and work it out. You should then plot it. You do that for all your values and then plot it, and you should have got something like this. Okay, I've tried to join it up as best I can. I've written my results, I have rounded them, and what we see is that this curve is not a straight line. In fact, it's known as a quadratic because it's got an r squared in it. But basically, this is, so I would say that A is not directly proportional to R. Okay, I don't get what I had before, and yeah, it's not a straight line. But what would happen if I plotted the curve of area versus r squared? Can you have a go at that and then make some conclusions, please? So in this case, you need to just take all your radii and you need to square them. So here I'd get 4, here I'd get 2.25, I'd get 1, I'd get 0.25, and I'd get 0. And what I wanted you to do was plot this against this and this against this. Okay, and they still fit on the graph when I square them. I've changed my axes to make it work. And what I get in this case is the following. I get a straight line, okay, because it turns out that area is proportional to the radius squared. So this is a slightly, a slightly more advanced look at it. It's not just about something equaling something times a constant. We still have the idea of direct proportion when I might be squaring. So I would write down that a is equal to k times r squared, and that k in this case is equal to pi. Okay, it fits everything. The fact that I've plotted r squared instead of r, okay, when I did it before for the volume of paint, because it fitted a straight line for the volume of paint, I could say that the price is k times the volume of paint, and I worked out what k was. Because it does it for r squared here, then I can say that a is a constant times r squared. And if I substituted back in or calculated the gradient, I would see that that gradient is pi. Okay, I've sort of set up this example knowing that I've already got the relationship, but it was just to sort of assist and give an idea and show that, this is not directly proportional, but this one is. Okay, so that's our conclusion. A is proportional to r squared. Now I'm going to bring in a little bit of notation at this point, okay, because you might think, you might have thought before, why do I need to have it? But what we do is we don't write it down in words, we do a little sort of a fish symbol, and we say that a is proportional to r squared. That is the same thing as me saying a is proportional to r squared. It follows from that a equals k times r squared. In this case, k is pi, but basically, if things are proportional, this is what's going to happen. You're going to write the proportional sign down, and then you're going to write a equals kr squared. So if I go back to my earlier example, I'm going to go back to the very first one. I could write down that y is proportional to x, and then it would follow that y equals kx. Okay, this is just a bit of notation to mean proportional, but it is important that you understand if I write that, then this follows, because we're going to talk more about that next lesson. All right, brilliant. So we've looked at two situations where we just get a nice straight line by plotting one thing that we thing against the other. And then we've looked at a slightly trickier one where it didn't, but then if we plot it against r squared, it does. In this final example, we're going to look at the idea of a pendulum. So a pendulum is a weight typically attached to a string, which is then connected to something that's holding it in place, and it swings backwards and forwards, and so on. Okay. We're going to assume here there's no air resistance, there's nothing stopping it, and it will just carry on going on forever. And what we're interested in is the time period for it to do a swing. So if I start now, okay, and I time it, I keep timing it, we're getting there, we're done. Okay, that would be the time that it takes for one period of the pendulum. And we might be interested in how this changes with the length of the string, and we could set up an experiment and we could measure it, and this is what I've done here. Okay, so I've got the lengths of string in meters, so 15 centimeters here up to 90 centimeters, and then I've got the time in seconds for it to swing. Okay, and we see that it increases. However, as L doubles, T isn't doubling. So L and T are not directly proportional, but there is a relationship between them, and we're going to see that by plotting T against the square root of L. Okay, and so what I'd like to do is, again, last one, set up some axes, work out the square root of L, plots t against the square root of L. Here is one that I've done earlier. So I've got my table and I've calculated the square root of L. There we go. Okay, in red, and then I've plotted it, and I've even joined a straight line. And what we see is that's pretty good, isn't it? You got to remember, in an experiment, you're not going to be exact. So some calculations, will be, you'll make little mistakes, and also, we'll make rounding errors potentially. If we're doing calculations, or when we're plotting it, we might not get it exactly right. So forgive me that they don't go exactly through it, but they're pretty close. And so you can say with some confidence that t is directly proportional to the square root of L. And then you could write down that t equals k times root L. We're straight away using, I've built this lesson up, and this is the sort of thing you should be happy with at this point, okay? It goes through the origin. Now, as I double root L, I double t. I can write this down. I could even try and find k as a number if I wanted to, but this is what I'm looking for, okay? The graph and this sort of idea here is where you should be at this point. Okay, it turns out that actually t is equal to 2 pi times the square root of L over g. Pi is the constant 3.1415, etc. G is the gravitational constant on Earth. So it's actually the amount, your acceleration as you fall, basically, from a height. This was discovered by someone called Huygens in the 1600s. And my question for you is, how could we use this formula to calculate a value for gravity? So I want you to pause the video in a minute and think about that. But before you do that, I just want to say that Galileo Galilei was his full name. He was one of the first people to study pendulums extensively before Huygens. He did it in the 1500s. That's a typo. He was unaware of this formula, but he still managed to calculate an accurate value for gravity. So in a bit, I also want you to investigate how he did that. Okay, it was thought by many that the sun went round the Earth, but Galileo thought not. He turned out to be correct, and he also managed to calculate the value of gravity. But first thing I want you to do is rearrange this formula to be able to calculate gravity. Right, so what we could do is we could rearrange it. T over 2 pi is going to equal root L over g. We could then square both sides. T over 4 pi squared. I've squared this t, this 2, and this pi, and that's going to equal L over g. I could now rearrange this. I'm running out of space, I'm going to come over here. I could write gt squared over 4 pi squared is equal to L. And then finally, I could rearrange this to make g the subject. I could multiply 3 by 4 pi squared. So g is 4 pi squared. Isn't it amazing that g seems to be linked to the value of pi? And then I would divide by t squared. So I could measure my length of string. I could do different pendulums and calculate the time period, and that would allow me to calculate gravity, something that you could do at home. It's quite an amazing idea that you can calculate gravity in this way. Galileo did it a different way, as I said. Just to summarize the lesson then, okay, directly proportional graphs are when as one increases, the other increases by the same percentage. Okay, as one doubles, the other doubles. As one goes up by 15%, the other one goes up by 15%. This is a more general way of saying it. We write it as this, y with a little fish sort of thing, x. That means y is directly proportional, and that means that y is equal to kx. That's the main thing you need to know. But just be aware, if y is directly proportional to x squared, then we can just put an x squared in there. Or if it was a square root, we change it to a square root. That is something you also need to know.